Hello, my name is Qiushi Bai. Today I'm presenting QueryBooster, improving SQL performance using middleware services for human-centered query writing. This work was done jointly with my colleague, Sadim Alsudeis, and my PhD advisor, Professor Chen Li at the UC Irvine. In today's data-driven world, business intelligence applications are extremely popular for business owners to make data-driven decisions. For example, Microsoft Power BI, Tableau, Apache Superset, and many more such systems. Usually, these BI systems adopt three-tier architecture. As shown here as an example, Tableau uses JDBC driver connects to PostgreSQL as a database. And a front-end application request from the user will be translated into a SQL query by Tableau. And the SQL query goes through the JDBC driver to the PostgreSQL database. The database executes the query, computes the result, and returns the result back to Tableau through the driver. Unfortunately, in our experiments and experiments from the literature, we saw that about 50% of the application-formulated queries, the database will miss the opportunity to optimize them. For one example, in the middle bar, we use Twitter Map as an application on top of PostgreSQL database. Among the 600 queries we analyzed, about almost 50% of them that Postgres missed opportunity to rewrite them into an optimized format or generate an efficient plan. This slide shows a concrete real running example. So we use Tableau to build a dashboard to visualize Twitter data on top of PostgreSQL. And the query on the right is an original query formulated by Tableau to compute a geospatial distribution per each state and show the distribution for iPhone-related tweets. This query took about 34 seconds to finish. Clearly, it was super slow. The reason why it was slow was because the plan generated by Postgres is a sequential scale. And the reason is it uses string position function call as the predicate to compute the tweets that contain iPhone as the keyword. Interestingly, if we write the query in this format, as shown on the right, we compute the iPhone-related tweets by using I-like predicate, not the string position one. The rewritten query is 10 times faster than the original one. The reason is the I-like predicate in Postgres actually can use the trigram index to do a faster physical plan. So the question is, where should we add this rewriting logic that we have already figured out? The first candidate is the application layer. How about we modify the code in Tableau to generate the query using the I-like predicate instead of the string position? Unfortunately, Tableau is closed source. We cannot modify its source code. The second choice, how about we input the rewriting rules into Postgres? Fortunately, we see that PostgreSQL does provide a rewriting rule language and an interface for users to input customized rewriting rules to write queries. However, the expressive power provided by the PostgreSQL rule language is too limited for us to express the rewriting needs specifically for our running example. We also studied other databases, and only MySQL and Postgres provide such interfaces for users to input the rules. And the same as Postgres, the input interface from MySQL is also too limited for us to express the rewriting needs as shown in the running example. Another question is, why not improve the query optimizer inside the database? An initial glimpse at the query, the running example, is that it's just another showcase of the optimizer misses one rewriting rule to further optimize the query. That is not true always. For example, one reason we cannot optimize we cannot improve the optimizer inside database to fulfill our achievements is because many rewritings that we identify are application specific or dataset specific. For this example, I show on the right, for this particular case, one predicate using predicate to do this keyword search on top of Twitter dataset using MySQL. If we rewrite it into the lower query using the match against the full text search predicate, it will be 500 times faster. And it is equivalent only for this particular dataset. It is not generally equivalent for other database or dataset. So for these domain-specific optimizations, improve the query optimizer inside databases will not work. Then we formulate our problem as the following. We treat application layer and the database layer as black boxes. How do we develop a middleware layer solution that allows users to express their rewriting needs? And our middleware layer can rewrite the queries on the fly to help the users to optimize their queries. In this paper, we propose QueryBooster as the solution. QueryBooster is a middleware-based cloud service for query writing. On the left-hand side, we have this online query writing phase. We provide a customized connector between the application and database layers. And the connector can intercept the query formulated by application and forwards it to the query writer provided in QueryBooster. And the query writer uses the rules formulated offline from the user to rewrite those online queries. On the right-hand side, we have offline rule formulation phase. The user can specify a particular rewriting rule using the rule language provided by QueryBooster, or the user can also provide rewriting examples. And a QueryBooster has the rule suggester can automatically generalize the user-given examples into rewriting rules. So to develop QueryBooster, we identify these two tasks. First is to develop an expressive and easy-to-use rule language. Second, we want to suggest general writing rules from user-given examples. First, let's look at the rule language. Before inventing our own rule language, we studied existing rule languages in the literature, as shown in this diagram. By studying them, we identify a few requirements for our own rule language. For one of the examples is that we want to utilize SQL semantics, which means our rule language should understand the SQL semantics such that the user doesn't have to specify them by themselves. For example, if we use regex as the rule language, it is very powerful and general. However, it is cumbersome for the user to specify a rewriting rule used in our running example, because the user has to specify those delimiters and symbols, keywords used in SQL semantics, and the users have to specify them by themselves. So we identified several requirements. For example, we need to understand SQL semantics, SQL schema. We need the rule language to be independent of any database or SQL dialects. And we want to minimize the additional knowledge needed by the users to use the rule language. And to summary, we propose a novel rule language called VAR-SQL, which meets all the requirements. So VAR-SQL is an easy-to-use rule language proposed in our QueryBooster system. This gives a high-level idea of the VAR-SQL language. The VAR-SQL comes from the meaning that we want the user to formulate a rewriting rule just as similar as to formulate a SQL query, as the pattern and the replacement. The only difference is the user can specify a column, a table, or a value as a variable, as shown in this example. A more complex example is shown on this slide, which says that besides a variable can represent a column or a table, we also have this set variable. For example, this S can represent a set of columns in the projection of a SQL query. And similar to other rule languages, we support constraints and actions to support more complex actions in the rewriting phase. To answer the question whether var SQL is good, we conducted a user study. In the user study, we compared the var SQL with the regex and another rule language at the logical plan level that is adopted by VTune paper. In the user study, we provide example rewriting from the original query Q to the rewritten query Q prime, and give the 3 rules formulated using the 3 languages, and ask the user to select which one is the easiest to understand. The result is shown here. As we can see, for all the 3 different cases, users from different backgrounds, 80% of them and even more selected var SQL as the easiest to understand the language, which shows the benefit of the proposed var SQL language. Second, let's touch briefly about the main idea of how do we suggest the rules from user-given examples. The goal is the user just to provide a set of rewriting pairs of the rewriting examples that the user wants to achieve. And we have a rule suggester can automatically generalize those query pairs into rules and output those high-quality rules that we think are appropriate to achieve the user wants rewritings. To give a high-level idea, how do we generalize a rewriting pair into more general rules? So we start from the query pair and introduce more variables gradually. In the paper, we defined several transformations that can generalize a rewriting pair or a rule. For example, this slide shows one of the transformations called variabilize a leaf, which basically means that we can introduce one variable to represent a column or a table name. In the paper, we have 3 more transformations defined to make one rewriting rule or rewriting pair into more general format. Now let's talk about the experiments. This figure shows one of the experiments in our paper that we did an end-to-end query performance improvement on top of TPCH dataset. We use Tableau on top of Postgres to do the analysis, and we use Tableau to formulate a dashboard for each of TPCH query to answer the business question. And we use VTune machine-generated rules to rewrite the query and measure the performance. And we also manually comes up with the rewriting rules to optimize the query. And then we use QueryBooster to implement those rules. And the y-axis shows the time reduction for those queries. As we can see, about 50% of the TPCH queries, QueryBooster can reduce the query time significantly. This is one example in the experiment. For the TPCH Q2 query, the shown query is the original query formulated from Tableau dashboard. And the original query took about 1.5 seconds to finish. And we identified 3 places that we can rewrite the query into a better format to make it better. And this is the rewritten query using the human-generated rule to rewrite it. And we can see the rewritten query only took 200 milliseconds to finish. To summarize, in this paper, we propose QueryBooster, a middleware solution for human-centered query writing. It enables users to rewrite queries for better performance. It provides an easy-to-use rule language, which is called VAR-SQL, and it provides a rule suggestion framework that can automatically generalize user-given query rewriting examples into more general rewriting rules. Thank you for your attention.